Okay, DC circuit part 4. In this section, we are going to combine transducer into our potential divider. So these are the learning outcomes. We'll be learning about two different types of transducer, namely the thermistor and the light-dependent resistor. Okay, so what are transducer? Transducer are actually electronic device that converts changes in the physical conditions such as pressure, temperature, or light into electrical signal so that it can actually be measured. Okay, there is a lot of transducer in our daily life. Okay, one example is a magnetic pickup is a transducer that picks up and converts the string vibration into an electrical signal in your electrical guitar. Okay, next. Okay, so there are two different types of transducer. One type is called the input transducer, and the other type is called the output transducer. So for input transducer, it converts non-electrical energy like light, heat, sound into electrical energy. So examples are your microphones, which converts sound energy into electrical energy, your thermistor, which converts heat energy into electrical energy, your light-dependent resistors, which converts light into electrical energy. There is also something called output transducer, which converts electrical energy into non-electrical source. So things are like a loudspeaker, which converts electricity into sound, your voltmeter, ammeters, and light-emitting diodes. But in our syllabus, we will only be focusing on input transducer. Okay, we will not be studying about output transducer. So input transducer, they converts non-electrical energy into electrical energy, and they are often used as part of potential divider to vary the output voltage as they respond to changes in the environment. Okay, so the first one that you're going to learn, okay, there are two that you're going to learn in this circuit, which is the thermistor. Okay, in real life, it looks like this. And the circuit symbol looks like this. It's like a resistor with a flat line and a slope up. Okay, it's not a tick, but it's just a flat line and a slope up. This is your thermistor, and this is the circuit symbol. And then your LDR, light-dependent resistor, the actual device looks like this. And the circuit symbols, is dependent on light. So it's like just a resistor with a circle, and then you have light falling onto it. So it's called light-dependent resistor. So both of them will convert non-electrical energy. In this case, is heat for thermistor and light for light-dependent resistor into electrical signals. Okay, for thermistor, there is actually two different types of thermistor. One is called the negative temperature coefficient, and one is called the positive temperature coefficient thermistor. But if the questions did not give you any information, okay, it is always assumed that it's a negative temperature coefficient. But most of the time, the question will give you information in the form of a graph or on a table. Okay, how does the resistance of a thermistor changes with temperature? Okay, but if it's not given, then we just take it as it is the opposite relationship, the negative temperature coefficient. What does it mean? It means that when the temperature increases, the resistance decreases. Okay, for this resistor, it's like a variable resistor, but it depends on temperature. When temperature increases, resistance decreases, or inversely proportional relationship. Okay, next. Okay, next we also have something called LDR, light-dependent resistor. Okay, for light-dependent resistor, it's taken as it always have an inversely proportional relationship. So as the light intensity increase, the resistance of the LDR decreases as well. So when one increase, the resistance decrease. Okay, so next, question. An LDR is used in a burglar alarm. Devise a simple burglar alarm that makes use of an LDR to trigger an alarm placed at the entrance door. Okay, let me show you the answer. Okay, you could use an LDR in this way. Let me explain to you how does it works. Okay, so if you have an intruder, that when the intruder comes into the door at the entrance door, it will block the light falling onto this LDR. Okay, so when the light intensity decreases, the resistance of the LDR will increase. And when the resistance of the LDR increase, the voltage across the LDR will also increase. When I have larger resistance, I need more energy to go through it. My voltage over here will increase. And if I were to connect a bell in parallel to this LDR over here, okay, when when there is light falling onto it, the resistance is low, the voltage is low, there is insufficient voltage to ring this bell or to trigger this alarm. But when someone passes through, a thief passes through, what happens? It blocks the light, the resistance of the LDR will increase. And since the bell is connected in parallel to the LDR, the bell potential difference of voltage across the bell also increases. And when it reaches a certain amount of voltage, the bell will actually ring. So when someone's passing through, the bell rings. So this is how a burglar alarm works. Okay, so let's zoom into more examples. With reference to the circuit below, describe how the voltage reading change as the light intensity decreases. So when the light, this is just not what I say, when the light decreases, resistance of the LDR increase. You cannot just tell me as light decreases, resistance increase, because I have two resistors over here. One is the resistance caused by the LDR and one is the resistance caused by the fixed resistor. So you need to mention the resistance of the LDR. Which resistance? The resistance of the LDR will increase when the light decrease. Okay, so when the resistance of the LDR increase, this voltage reading will also increase. Or this one can be connected across. How can it be used? It can be used in straight lights. Okay, so when the light decreases, okay, the voltage increase, we'll connect this to a street lamp. This street lamp will start to light up because it will have sufficient voltage. So it will automatically light up when it gets very dark in the evening. Okay, so this is how it works. Next question. Okay, figure 17.28 shows a resistor of 10 kilo ohms connected in series, okay, with this LDR. This LDR has a resistance of 500 ohms in bright light. What is the output voltage and the current flowing in the circuit? Okay, so I want to find this V out. Okay, so I need the resistance here over the total resistance times 12 volts. This is the formula for the potential divider. Okay, so the first step, output voltage will be 500 over 10 kilo ohms is 10,000 ohms plus 500, the total of it, times 12 volts. So it's 0.57 volts. Okay, so that is the output voltage. And what is the current flowing in the circuit? I equals to V over R. So I have 12 volts is for the whole circuit over the total resistance, which is 12 over total resistance, 10 kilo ohms plus 500 ohms. So that is my current milliampere. Okay, second question. In dim light, the LDR has an output voltage V out of 8 volts. How much is the resistance of this LDR in dim light? Okay, so now I need to change a little bit. I know my V out is 8 volts. So I'm going to apply the same formula. Okay, so 8 volts will be equals to, I don't know how much is the resistance of the LDR, R over R plus 1 or R plus 10,000. Okay, 10,000. Okay, 10,000 to give me 12 volts. It means in. Okay, so it's R of the resistor over R plus 10,000. I get times 12, I get 8 volts. So if you were to solve for your R, you get R is 20 kilo ohms or 20,000 ohms. Okay, next. This diagram shows a circuit diagram of a kitchen stove heat sensor. If the stove temperature is kept at 300 degrees for more than 30 minutes, the thermistor will be heated up to 300 degrees. And when this happens, so when the temperature increases to 300 degrees, the resistance of the thermistor will fall from 2 kilo ohms to 100 ohms. The supply voltage over here is 15 volts, and the resistance of R1 is 1.9 kilo ohms. Okay, what will happen to the output voltage over here? So this one, as the temperature increase, okay, when the temperature increase, the resistance drop over here. from 2000 ohms to 100 ohms. As the resistance drop, the voltage across the thermistor will also drop. So the V out will increase. Okay, so it's as follows. Okay, you may use some calculations because the questions did give you number. So initially, when it is not hot, it is 2000 ohms. So I want to find V out will be 1900 over 2000 plus 1900 times my total voltage, which is 15 volts. So originally, when it's not hot, V out will be 7.31. But when the temperature rise up to 300 degrees, the resistance of the thermistor drops to 100. So now I'm 1900 over 1900 plus 100 times 15. I get 14.3. So the V out actually increases when it's very hot. So suggest how this circuit can be used to detect if a stove has been left unattended. Okay, so my V out actually increases from 7.31 to 14.3. So I can easily attach this V out to a light bulb or to a bell. So when the temperature has been left on for some time, 30 minutes, okay, this V out will increase to 14.3 and it will then activate either the light bulb or the bell. So it can be connected to a warning light or a bell, which will then be triggered, which will light up or which will ring. That tells you that the stove has been left unattended for some time. It has been heated up. Okay, next example. Okay, this is a simplified circuit diagram of an automatic straight light controller. So you have a V out over here, which is attached to a LDR. The voltage V out needs to be at least 12 volts in order to turn on the street lamps. During the day, the resistance of the LDR is 100 ohms and the supplied voltage is 15 volts. Okay, so let me key in all the values. Okay, supply voltage is 15 volts, resistance of R1 is 27 kilo ohms, and the resistance of the LDR is 100 ohms in the day. Okay, then you need to explain why the street light does not turn on during the day. So I need to calculate the V out over here, which is attached to the street light. So if I want to calculate the V out, I'll take 100 ohms divided by 100 plus 27,000 ohms, total resistance, times 15 volts. Okay, so you work out, you will see that the V out is 0.06 volts in the day. 100 over 27,000 plus 100 times 15. Okay, since it is less than 12 volts, the street lamp will not be turned on because the street lamp will only be turned on if it is more than 12 volts. Okay, let's come back to here. During sunset, now the resistance of the LDR increased to 1 mega ohm. So now I'm no longer 100, I become 1 mega ohm. Okay, and this will cause the street lamps to be turned. This will actually cause the street lights to turn off, to turn on. Okay, let's check. Will the street lights be turned on? Okay, so now again, I want to calculate this V out, whether will it be more than 12 volts. I use 1 mega is times 10 to the power 6, 1 million ohms plus over 1 million plus 27,000 times 15. Okay, if I were to calculate, it's over here. So I have 1 million over 1 million plus 27,000 times 15, I get 14.6. Yes, now V out is more than 12 volts. So yes, the street lamp will be turned on in this case. Okay, let's go back to part C. Okay, it was found that when the street light turns on, okay, so once the lamp is turned on, it reduces the resistance again. Got light, then the resistance of the LDR will drop again. Okay, when the resistance of the LDR drops, the voltage across it drops and the street lamp turns off again. Okay, in the absence of light, the street lamp turns on again. So this cycle keeps repeating and the street lights keep turning on and off. So how can we prevent this? Okay, one very simple way is to ensure that the light from the street lamp doesn't affect the LDR. You can put anything that blocks the light from the street lamp to the LDR or simply place the LDR on top of the street light so that the light will not be able to reach the LDR. Okay, Once the light cannot reach the LDR, it will not affect the resistance of the LDR, and the straight lamp will not be switched on and off continuously. Okay, that's it.